Hi everyone. Last time we talked about the pipeline data path and pipeline control. Today we'll discuss about pipeline hazard, particularly data hazard, and the corresponding solutions are called forwarding and stalling. So the same slide we shared the last time, the subtree instruction is followed by AND instruction. There is a data conflict, data hazard regarding register 11 because in cycle 5, the updated register 11 is already available. On the other hand, AND instruction wants to have that the newer value of register 11 in ID stage. So because of the time conflict, we have to insert the two store cycle to delay the pipeline. So that will really undermine the advantage of the pipeline architecture. So this is called the hazard, pipeline hazard. There are three types as discussed last time: structural hazard, control hazard, data hazard. Data hazard has something to do with the data conflict. Control hazard, something to do with the branch instruction. Structural hazard is a resource conflict. So regarding the data hazard, so the solution is called, one of the solution is called the forwarding, or you can simply consider it as a data feedback. So if you look at the chart at the figure at the bottom, the newer value of register 11 is going to be updated in write back stage in cycle 5. On the other hand, the newer value of register 11 has been calculated during the execution stage and ALU. So in cycle 5, at the end of the cycle 5, the data is already available, although it is not written to the destination register 11 yet, but the data itself is available. In AND instruction, in fact, it is reading the register 11 in ID stage, but actually it needs the data in execution stage in cycle 4. If you're counting from the top, from the beginning, it is just cycle 4. So as long as there is a proper data path, kind of a data feedback mechanism in place, probably we can avoid the pipeline delay. That's basically the idea behind the forwarding. So let us assume the subtree instruction in ID stage, and it is a reading the source register 3, register 2, and we assume register 2 has the value of 200, register 3, 300, register 11, 1100, for example. So the source register, the 3 has been read and it is a 300. Destination register 11 is at the bottom, it is carried to the next stage. In the following cycle, what happened is that subtree instruction is moving into the execution stage, 300, and register 2 is not shown here, but that's a 200, and it is a subtract instruction. So output is going to be 100 from the ALU. The output is a 100. On the other hand, in ID stage, what happened is that since it is the AND instruction and reading two source register 11 and 4, so first the source register 11 is register file is read and get the value of 1100, right? So that's basically the assumption. And at the bottom, the destination register 12, and in execution stage, destination register 11. So, as discussed last time, destination register number is a carryover from stage to stage. In the following cycle, now the subtree instruction is in memory stage and the instruction in execution stage. What happened is that the register 11, one of the source register in execution stage, has been read in the previous cycle, which was 1100. So it is carried forward to the execution stage. On the other hand, as you know, the newer value of register 11 is not 1100, it's 100, because previous instruction, subtree instruction, compute the register 3 minus register 2. The result is 100. It is just supposed to be written to register 11, but although it hasn't been done yet, but we know that the result is 100. So new value of register 11 is 100. So now we have an issue that the ALU execution stage ALU, the value from the ID stage is 1100, but it must be 100. So the idea is that why don't we just get the data feedback? We already have the line U, which carries the 100 value, which is the new value of register 11. So why don't we get some additional data pass, right, from the memory stage to the ALU so that we can get the proper data. Of course, there must be some additional control because there are two input to the first source to the ALU, one from the register file, another from the feedback data pass from the memory stage. So there must be some control, but using this additional data pass or forwarding logic or some feedback, we can avoid the pipeline delay. Likewise, if the subtract instruction is in write back stage and there's a typo, that must be write back, and OR instruction is in execution stage, and one of the source register is register 11, write back stage, the register 11 is the destination register. So the same thing, the new value of register 11, 100 is already available in line G in write back stage. And we can have an additional data pass to the execution stage so that the ALU can have the second source data for the OR instruction. So this is just the additional data pass. It can be the additional data pass is coming from memory stage and write back stage, and it can be the feeding into the first source of the ALU or the second source input to the ALU. So there are four additional data pass, and the question is, of course, how do we control the additional data pass? We need to have a probably additional multiplexer in front of ALU. So here's what it is. In front of ALU, there are two additional multiplexers. And if you look at the first source to the ALU, there are three input. One input is coming from register file. And in terms of a multiplexer, it is 0, 0. And another data pass, another candidate is feedback data from memory to write back stage, multiplexer value of 0, 1. And the last one is another feedback from the memory stage. That's the multiplexer value must be 1, 0. So that particular, the multiplexer control signal is called a forward A. And likewise for the ALU source number 2, we need the additional multiplexer and the corresponding control signal called the forward B. So at the bottom in execution stage, there's a small, red colored the circle. That's a forwarding unit. So forwarding unit is getting some input and producing two output signal, forward A and forward B. So the forwarding unit at the left bottom corner, forwarding unit is essentially 6 input, 2 output, the combinational circuit. So 2 output means forward A and forward B. Regarding those 6 input, we'll discuss in the next slide. So how do we make up, what is the inside of the combinational circuit of the forwarding unit? So if as we saw in the previous slide, in order to get the feedback from select the feedback from the memory stage, that must be 1, 0. Write back state is a 0, 1. If you get the value directly from register file, it must be 0, 0. So this is just a rough sketch of the control logic, forwarding control logic, and which is the same case for the forward B. So forward A and forward B, the only difference is that forward A is take care of the first source of the ALU. Forward B is a control signal for the second source of the ALU. So now we look at the conditional part. So conditional part in forward A 10 if EXMEM-LD is equal to IDX-LS. So if you look at the small graph at the top right corner, let us assume execution stage is executing AND instruction 12.11.4. Memory stage is executing subtract instruction 11.3.2. So memory instruction, the subtract instructions, the destination register is 11. So RD is 11 in memory stage, and RS in execution stage is 11. So AND instruction 11 is the source register. So if RS in execution stage and RD in memory stage is the same, that satisfies the feedback condition. So if that happens, you need to get the value from memory stage rather than register file. So that is what it is. So if you look at the equation again for the A10, if EXMEM-LD, so that's subtract instruction 11, and IDX-RS, that's actually means the AND instruction register 11. So if that's the same, the condition satisfied, we're going to get the feedback from memory stage, right? Similarly, if the similar condition satisfies, then we get the feedback from the write back stage. Otherwise, we get the value from the register file directly. So now another complexity comes from the fact that when the execution stage is executing AND instruction 12.11.4, memory stage is executing stored instruction 11.05, the RS in execution stage is 11, memory stage it is actually RT, but the RT and RD in case of a load word instruction, stored instruction, it is interpreted as a RD. So in this case, this is the same, but as you know, the stored instruction is not intended to write into the destination register, so you don't really need a feedback at all. So you need to make sure that the instruction in memory stage is supposed to update the destination register or not. So that's why we have the EXMEM register write. That's an additional condition in order to get the feedback. Just one more complication, as in the example, OR instruction in execution stage, one of the source register is 11. Now the memory stage, the destination register is 11. And unfortunately, write back stage, the destination stage is also 11. So RT in EX and RD in memory stage is the same. Also, RT in the execution stage as in the same as RD in the write back stage. So since the condition is satisfied in both places, you may want to get the feedback from both places, which is obviously not possible. But as you see, you need to give the preference for the later instruction, because later instruction gives you more up-to-date data. So that's why we have an additional condition, which the circle. So that's basically the forwarding logic, complete forwarding logic. So you can have a multiple input into the forwarding logic, so you can come up with the corresponding combinational circuit for forwarding logic. And this shows the overall picture. So that's and it definitely shows the 6 input into the forwarding unit. Thank you.